I'd like to remind you that for more Microsoft webcasts, you can go to microsoft.com/webcasts. Thanks again for joining us for today's presentation, Windows Communication Foundation Top to Bottom, Part 13 of 15, Transactions. Now it is my pleasure to introduce today's presenter, Michelle LaRue Bustamante, who's the Chief Architect with iDesign Incorporated. Michelle, you now have the floor.
Thank you, Heather. Welcome, everybody. So here we are for Part 13 of 15, our series on WCF, and today we'll be talking about transactions. So again, my name is Michelle LaRue Bustamante, and for those that I have not had a chance to meet yet on these webcasts, my primary role is with an architect at iDesign and doing training and consulting, and then I'm also a Microsoft Regional Director for San Diego. The most important thing on this slide that you care about, of course, is that indigogirl.com, my weblog at the bottom, is where I've been posting, well actually, it's where I've posted all of the code for my book, Learning WCF. And then I have another blog, theswan.net, where I periodically post additional items related to WCF card space and other things that I do. So you want to make sure that you go to at least that Indigo Girl to download the book code, and if you have any questions, you're free to email me, and you can contact me through either website. So today what I'll be talking about is the implementation of transactional programming within WCF. And again, the focus here is really on distributed systems, the idea that when I am working with services, I'm really replacing previous concepts that we were used to working with, like remoting enterprise services and, of course, web services. And now, with WCF, we have a single programming model for all of those behaviors. And, of course, within that, we also have the ability now to do transactions across any of those types of boundaries. So that's what I'll be focusing on. And of course, to support this over HTTP, we need standards. And so there are some underlying web service standards that support that interoperability between other platforms and WCF so that we can achieve transactions across those types of boundaries as well. And then, of course, the focus of this will be to give you an introduction to the configuration options that you need to know about in order to enable transactional programming across those service boundaries, regardless of if you're using TCP or named pipes, or if you're working with web services, for example. And then as for MSMQ, queued messaging, yes, those do also support transactions, but I'll be talking about that in the webcast after this one today, so you might want to stay tuned for that as well. So today what I'm expecting is that you are familiar with .NET programming, of course, and the framework, and that you have a basic understanding of how to work with WCF clients and services and the associated configuration settings to get started. Of course, this is a long series, so you can always go back and play the entire series if you're not familiar with these things. And on my weblog, I do have an entry that lists all of the webcasts in the series, so you might want to check that out if you haven't already. As for the exact agenda, we'll talk again about the reliability features available to WCF. I'll get into why we care about transactions. We'll talk about the transaction managers available, just so that you have a high-level understanding of that if you're new to the topic. And then, of course, I'll dive right into the configurations for WCF specifically. So if you are new to the concept of transactional programming, I guess what I would say is I'm going to give you a crash course in 15 minutes or less. And you may still have some questions about that, but at least then it'll give you a foundation for the WCF specifics. So when we talk about reliability in a system, so again, thinking distributed, service-oriented systems today, we need to make sure that when we talk to remote application functionality, whether it's exposed through some component, like a COM+ component in enterprise services, or whether it's a web service, any type of distributed functionality should be somehow predictable in that we know it was called, we know it executed successfully or not, and we can react if it doesn't. What we want is for the system to be available, those services to be available and reliable, but we also want to make sure that we leave the system in a consistent state, meaning if some part fails of an activity, we shouldn't complete part of the activity. We should complete everything as a whole unit. And then we also want to make sure that we can overcome issues with network connectivity to reach those remote services and functionality as well. Of course, like I said before, with WCF, we're really sort of phasing out enterprise services, remoting, and classic web services with ASP.NET. And we're using WCF for all of those things. So we think about those as service boundaries. Don't confuse that with a web service boundary. It doesn't have to be a web service. And with that service boundary, we have the ability to overcome each of these reliability issues using the collective features of reliable sessions, transactional programming, and queued messaging. Now, I talked about reliable messaging in the last webcast. And in that webcast, we talked about how we can overcome interim problems with network connectivity and have the client retry sending messages. And that's all done at the low-level channel layer. So WCF handles that for us if we enable reliable sessions. When we talk about transactions, we're actually dealing with a different problem. So what we're thinking about with transactions is the ability to coordinate activities as a single atomic unit of operation. So we want to make sure that if I need to update 3 separate tables and generate an email and save a file to disk, all those things happen as one operation, and if any part fails, we roll back the whole operation, and so therefore the system is consistent. Now, the way this is accomplished is with transactional programming, and this has been around since the 60s and 70s, of course, so all of the plumbing related to making sure that transactions get coordinated properly is built into transaction managers and resource managers in the respective platforms that we use. And so the idea is that I shouldn't have to write all of the code to coordinate, hey, did all of these things work? And if not, let's roll them all back and handle collecting all of those votes and so forth. So I'll talk about that a little bit further, but the point being we want to make sure that everything happens or does not happen, and we don't want to write a lot of complex code, if-else statements, catching of exceptions, because we can't possibly manage all of that across distributed environments, for example. So either everything succeeds or everything fails, and that's the simple idea around transactions. Too difficult to coordinate all of this when you have a bunch of different components that really only know about their activity. They can't possibly know, did the rest succeed or fail? They only know, did I succeed or fail? So that's the idea of transactional programming. Now, the classic properties of a transaction are that it is atomic, consistent, isolated, and durable. So atomic meaning everything is completed or not as a whole. It's an all or nothing proposition. Consistent meaning that we never leave the system in a state where parts were successful and parts were not. So we shouldn't be able to view table 1 with a record that was inserted if the coordinated update to table 2 was not completed. And then isolated really just means that if you have different transactions going on, maybe because it's a multi-threaded application, maybe because you have many clients calling into server applications, each of them respectively protects their own resources. So if two transactions try to talk to the same tables or records, then of course only one can get in at a time. They need to be isolated from each other in some way. And of course you decide what the isolation level needs to be. They need to be durable in the sense that it should be able to survive a restart of machines, because what happens if one of the machines performing the activity goes down or the services need to be restarted? It should be that within the transactional programming model, the server machine that went down, when it's restarted, has memory about the transaction and the state of it, whether it was successful, whether it was not, and therefore can still communicate with the coordinator of the transaction when it comes back online. So ACID properties are classic description for transactional programming model. Another thing you need to be aware of is that all of this happens between a coordinator, so obviously there needs to be some hub that's responsible for, did everything succeed or fail? And what should we do next? And this is handled with two-phase commit protocol, whereby all of the participating resource managers, so that's another thing that you should be aware of, is that, for example, a database like SQL Server is a resource manager. meaning it knows how to communicate with a coordinator, and there are standard protocols for that. And I'm not talking about even web service standards here. I'm talking about protocols for communicating with, for example, a distributed transaction coordinator like Microsoft DTC. And so resource managers communicate with a transaction coordinator to indicate to join a transaction. If the coordinator says, would you like to join this transaction? And the resource manager opts in. And then, of course, if the coordinator says the transaction should be aborted, then the resource manager should comply. So what happens in phase one is the coordinator asks each resource manager involved in this activity to commit. And that would mean, of course, in the case of databases, to write to the table. But it's done in a tentative way such that we know, could it be successful or not? And the resource manager indicates to the coordinator, yes, it could be successful, or no, I'm not going to be able to do that. Coordinator collects those votes from all the different resource managers, which again could be spanning multiple machines, could be spanning multiple resource managers, different databases even. And the coordinator, having collected those votes in phase two, will ask the resource managers to commit or abort collectively. And if it asks them to commit, it expects an acknowledgement back to indicate whether it was successful or not. So this is just a simple overview of what we expect to happen with transactions. We expect two-phase commit protocol to be executed, and we expect the coordinator and the resource managers that we do not have to code to participate in those activities. Now, our programming model needs to be much simpler in order to make this manageable, and that's what I'm going to get into. There's also another concept, and that is that with SQL Server, for example, it's a durable resource manager, meaning it's able to persist the state of its participation in the transactions, such that if we restarted the database server, when it comes back online, it remembers that, hey, I was in the middle of this transaction. Here are my list of transactions that have not been completed. And this one, you know, each of those states basically are kept alive, and then the coordinator can later find out the state of the transaction when the resource manager is back online. So the idea is that with a durable resource manager, or RM, which is my short term here, they will be able to survive server restarts. There is a concept called volatile resource managers, which is something done in memory. In fact, when .NET 2.0 was introduced, System.Transactions was introduced, which made it possible for us to create classes like transactional dictionaries, transactional integers, if you like. And we have a utility on the iDesign site that was written by my colleague Yuval Lowy that actually gives you the ability to create any type as a transactional type. It's a generic extension. So you might want to take a look at that. Just remember the main website from this webcast, iDesign.net, which is our company site. At any rate, volatile resource managers really just means that you have some class or dictionary or something that when you want to save changes to it, if it's part of a transaction and something goes wrong, you want to be able to roll it back. And that's a .NET 2.0 feature. Again, nothing to do with WCF, but something you should know about, because in theory, if a transaction should be performed atomically, then that should include volatile memory resources as well as durable resources. Now, how do we create a transaction then? And you will probably be familiar with this syntax if you're familiar with .NET 2. We can wrap code in a transaction by using the transaction scope. And this is a simple way to say, look, this block of code should be completed as an atomic operation. Now, of course, I'm only worried about these couple of operations in this particular block of code, but operation 2 could have its own transaction scope that does a whole bunch of other things as part of a transaction. And it may not know that I'm including it in a top-level root transaction. So the idea would be that nesting is possible, and that in most cases, all of the downstream code will join the root transaction if there is one. Otherwise, it creates its own. And I'll talk a little bit about that at the end of the webcast just to give you some visuals on where transactions might live and how should we approach writing code like this. But again, this is .NET 2 stuff. This is how you create or initiate a transaction in client code, let's say, to call down to a number of services. And it's part of .NET 2.0 in System.Transactions. Now, let's talk about the resource or the transaction managers available to us when we create the various, when we create a transaction from the client. Let's actually take a look at the different transaction managers that are available. So the Lightweight Transaction Manager is basically a transaction manager that is available with all right, so the Lightweight Transaction Manager is basically introduced with .NET 2.0, and what it allows you to do when you create a transaction scope and you call, let's say, a couple of operations, and never mind services at this point. Let's say just within an application domain I have a couple of methods that I'm going to call, and each of those methods, let's say represented by the gray boxes here, might have a job to do. One of them could call down to SQL Server to update a database table, and the other might talk to two in-memory volatile resource managers, let's say like a transactional dictionary. And so what's going to happen is, by default, when we create that transaction scope, as long as we only call one durable resource manager and we stay inside the application domain and don't cross any app domain or process or service boundaries, we will actually only be using the Lightweight Transaction Manager. Now, what does that mean? That means that I don't use the Distributed Transaction Coordinator, which creates some overhead to coordinating a transaction. So it's just performance improvement for simple transactions. Now, with Vista and with, of course, Windows Server 2008, the Kernel Transaction Manager was introduced. And the Kernel Transaction Manager basically supports a transactional registry and a transactional file system, so that if you want to, say, write some updates to the registry as part of a transaction that also coordinates some volatile resource managers, and you stay in the same app domain, and you only talk to one durable kernel resource manager like the registry, then you will only use the Kernel Transaction Manager on the machine as opposed to the Distributed Transaction Coordinator, which carries more overhead. Through a process called promotions, your single transaction scope will automatically promote you from the Lightweight Transaction Manager to the Kernel Transaction Manager if you need it, because you called to the registry. Now, the minute you leave the app domain or call to multiple durable resource managers, you will end up being promoted to the Distributed Transaction Coordinator. Again, you don't change the code. The programming model stays consistent for you because the underlying system.transactions model knows how to do promotion, and as long as the transaction manager supports promotion, then it's going to work. And so, of course, these do support it. So when we cross an app domain, a process, or a machine boundary, or a service boundary, then we will end up automatically using a Distributed Transaction Coordinator to collect votes for all the various participants in the transaction. Now, what does that look like? If you're not familiar, the DTC is something we enable on each of our Windows boxes. And so whoever starts the transaction, the machine that starts the transaction, the code that initialized the first transaction scope, will become the root DTC. It will become the coordinator. And then what happens is, let's say I cross a service boundary to machine C and machine B from the root. Then the Distributed Transaction Coordinator on each of those machines will collect the votes for their resource managers, like the two SQL servers down here on machine C, or the transactional registry and file system on machine B. And they will report their findings back to the root, of course, as part of the coordination process. So what happens is the DTC automatically has a bunch of RPC messages that fly back and forth to make sure the votes are collected, to make sure that each of the resource managers on those other machines are eventually told what to do. Do we commit or do we abort? Now, this is all automatic. But what we need to know, of course, is that this just works and that WCF will leverage the DTC for us where appropriate. Now, there's also some interoperable standards that have been introduced for transactions. In fact, they were just ratified this year in April 2007. And these are web service standards that allow us to, over HTTP, do messaging like the RPC messages that the DTC does, but interoperable. And that means that we could have a Java equivalent of a coordinator and a equivalent on another machine from a different company or a different application that is the DTC with these standards enabled. And they would be able to participate in the same transaction. One of them will be the root and be the coordinator, and others will be participants. So what happens is these standards, WS coordination and atomic transactions specifically, together make it possible to do a distributed, short-lived transaction. Business activity is another specification for longer running transactions that we'll not get into here. Now, the transaction standards allow us to do transactions over HTTP across platforms. So the WS Atomic or WSAT allows you to do a reasonable unit of work that's short-lived, isolated, and durable. When we talk about business activity, we're talking about compensating transaction and logic, like a workflow. So how do we work with WSAT in our environment with Windows operating system and WCF? Well, what happens, first of all, we haven't talked about how to enable transactions in WCF, which is just coming up next. But the underlying protocol of WSAT has to be enabled in each of the respective DTC if you plan to use HTTP between these machines. So the exact same communication actually goes on. But if one of these machines were to be replaced with a Java implementation of a coordinator instead of the DTC, then we would need to use WSAT to communicate with it instead of RPC. What happens with the DTC is that if all the machines are Windows boxes with the DTC, even if you are doing HTTP, in order to improve the performance of the communication between the machines, there are also the RPC messages sent between the different DTCs in the transaction. And that makes it possible for us to be interoperable if needed, if one of the boxes was Java, let's say, Java implementation on top of a non-Windows box. So to enable the WSAT, what you have to do first for any of this to work, and I talk about this in one of my labs in my book, but these are the short steps for you. You have to call reg assembly and pass it the WSAT UI DLL. And you can find that in the SDK for .NET 3.0. And then you have to go to the DTC, which is available through the Component Services snap-in. And you have to go in and explicitly enable atomic transaction support. Now, to do this securely, you do it over port 443, which means you have to provide certificates so that the machines can authenticate one another, and that will, of course, reduce the risk of malicious callers participating, let's say. You also have to enable network DTC access if you're doing anything outside of your own machine. So when I do a demo here, I don't need network DTC access. But if I am crossing machines, then I need to do that. And you have to decide if you're allowing inbound and outbound. So, of course, you would want that if you're doing DTC communication. And then also you can enable authentication in a production environment, which would use the certificate. So those are the key things you just need to be aware of. But in order just to get started and productive and test out some demos and things so that you can try this out, basically what we're saying is that you need to enable install WSAT in the DTC and then enable it, not necessarily for network access or security, just to get started, but those are the features you'll hear about later. Now let's move on. So what I've done so far is sort of giving you an overview of, why we care about transactions, how do they work in .NET 2, and what is this promotion thing. So I write a transaction scope. I create a transaction from a client, let's say, And what I'm expecting is that all the code I call downstream as part of that wrapped root transaction will actually just do the right thing. If I need the kernel transaction manager, it'll promote it. If I need the DTC because I'm crossing machine boundary, it'll promote it. If I need the WSAT because I'm calling a service that only supports that, then it'll use it. And what I need to figure out is how do I make it possible when service boundaries are involved to have a client make calls and enable transactions. So in fact, the features here, the things I'm about to go through in a demo, is to enable transaction flow on a binding, to make sure you know your transaction protocol being used, to tell the service operations to support transactions and basically decide what level of support you require. And then each service operation implementation must decide if it would like to join a client transaction or create itself. So with that, let me go through a demo, and we'll sort of go through each of the steps one by one. So in this example here, I have a service. It's got a number of operations, resetting counters. I've got two calls to update two separate counters, so they're two separate tables actually, and then a call to get the counters back. The logic for the data access is ingrained in this counters data access component, and of course, there's no transactions right now. So basically, I'm expecting both of these set counter calls to work. I'm expecting this individual call to set a counter to work, and so on. Now what the client does, and let's just go ahead and give it a run. So I'm going to start the host, and I'm going to start the client. Client will call get counter and retrieve the counters. It can call set counters and set the counter. I can reset the counters to 0. I can set the counter to any value. And if I try to set the counters to 12, what's going to happen is the first counter will succeed because it's allowed to be set to that value. The second counter, though, counter 2, cannot exceed 10. So an exception was thrown by the data access layer. And so the second counter could not be properly incremented. And now I'm inconsistent because I tried to update both counters together, and I couldn't keep them synchronized. The client code that did that is right here. So we're going to actually go into the set function. And you can see that I'm basically calling two separate calls to set two separate counters. And if I want them to stay synchronized, I need to do that as part of a transaction. Otherwise, I would need to check the value of the counter, see if it was correctly updated, and if not, roll back the first one. So that's not really desirable, especially since this is just a simple example. Imagine if it was more complicated. So if I set it to a legal value, everything's good. If I set it to an illegal value, something goes wrong, the first counter gets updated, oops. If I set it to an illegal value greater than 20, then the first counter set will fail because the first one cannot exceed 20. And then, of course, they both say not set. But it's not because I had a transaction, it's because by fluke, of course, the first failed, so this line of code failed, and I never got to the second line of code. So you get the idea. We need a transaction. So let's take a look at how I would enable the transactions for this. Let's just start with the fact that I'm hosting that service over, currently, TCP. And in there, what I've got is a net TCP binding with transaction flow set to false, that's the default, and OLE transactions, which is the protocol we're using, which is really just saying DTC RPC. So I'm going to enable transaction flow on the service. And what that means is I'm allowing clients to send me a transaction, and I will participate in it. Well, I'm not finished, though. That's just the start. Now let's go to the client config. Again, transaction flow is false. Let's set it to true. Now, the other thing that we need to do is to create a transaction scope in the client. So let's actually go ahead and do that. What I want is for these two guys to be wrapped in a transaction scope. So I'm going to say using transaction scope and I'll create a new scope. And the default behavior for the scope is to, let me just, scope options. The default behavior is to use required. What that means is, if there's a transaction above me, then I'll participate in it. Otherwise, I'll create a new one. And that's usually the feature that you want, usually. So, in this case, we are the root of the transaction, and we now have one. Now, before this will work, of course, I have to scope complete to make sure that if everything is successful, no exceptions happen, we vote to commit. Okay, so now I have a transaction in the client that I'm going to hopefully flow to the service. Now, what we also need to do is at the service indicate our level of requirement for a transaction. So what I'm going to do is I'm going to start with just looking at set counter 1 here, and I'm going to add an operation behavior. And what I'm going to do is set the transaction scope required. And I'm going to set that to true. I'm going to also set the second counter to require a transaction. So what does this mean? This means that if I receive a client transaction, I will join it. Otherwise, I'm going to create a transaction for this operation. And by default, it will actually vote to commit because by default, transaction auto complete equals true as well. So this is equivalent to this. Okay, so what we have now is what would seem to be a client transaction that will indeed flow to the service, and that the service says, I want to join that transaction. Let's see what happens. And actually, I will restart the service, so let's shut that down first. And let's start the host up. And let's start the client. And so the counters are currently 0. I'll set them to 5. Looks like that worked. Let's see if we can recover from a transaction failure. And it looks like we failed, right? And of course, it didn't work. Now, the client actually did not flow a transaction to the service. And the service would not receive a client transaction in its current state because we're missing one step. And that is, in the actual operation contract, I need to set the transaction flow attributes, and the transaction flow options I'm going to set to mandatory. Actually, I'll make it not mandatory. I'll just make it allowed for now. Allowed means if you have a transaction from the client, it's okay. If you don't, then okay. And I'll review these things in a moment. Now, let's go ahead and restart the service again. And this time what I'm going to do is actually go to a browser. And with metadata exchange enabled on the service binding, what I can do is view the WSDL. And what you're going to see here is that there is actually a description in here that says we have transactions enabled and that we're saying it's optional. Set counter 1 has an optional transaction. These are web service protocols describing officially in the web service description language so that when you generate a proxy, it will properly respect the settings. So look what happens now when I go to my client and I say I want to update the service reference. It will download the new WSDL. It will update the client proxy. And now guess what? The proxy is going to have and we'll just open this up so that you can see the proxy code. The proxy interface, iCounterService, will indicate transaction flow allowed. That is what will officially send the transaction to the service. So in fact, at the client, I need three things. I need to enable flow on the binding. I need to allow it at the operation or make it mandatory. And I need to have a transaction. We now have those three things. At the service, I also need four things. I need to enable flow on the binding. I need for the operation to indicate whether we allow or require a transaction. I need for the operation implementation to join the transaction if I want to be part of it. And that's that. Okay, so let's run it again. The service is now running, so let's run the client. Oops. That's just a different issue because I updated the service reference. And so now I have actually multiple endpoints and binding configurations. So we need to choose which one we want. It didn't want to delete the one I already had. So what we'll do is we'll call this one NetTCP. And I think I'll just get rid of this one altogether. And we'll call this one NetTCP. And then as far as the bindings are concerned, we'll keep this one, NetTCP. This is the one that was just created, the latest. And I'll delete the first one, and away we go. Now because I only have one, I can start the client, and it'll pick up the only endpoint we have. Okay. Now the counters, I'll reset them first. I'll set them to a good value so that we can see that we're making calls to the service successfully. And now let's make a bad value. We get the exception. And it looks like it rolled back because we weren't able to see the update. And we'll set it to a larger value. Again, nothing happens. Okay, so transactions work. I guess that was the theme of that. Now let's talk about some details. And I'll just check and see if there's any questions in the queue. Okay, so somebody's asking, is a one-way call a non-blocking call by default? Okay, so I don't know, this isn't really related to transactions, but I guess I would say if you mean can I send multiple calls to the service from the same proxy if it's one way, the answer is yes, because when the call reaches the service channel, then the client is released, and so another call can come in without multi-threading. So if that answers the question. Somebody's asking what's available on Vista. In Windows Vista, we have the Web Service AT, so Atomic Transactions is available. You can enable it. The DTC, of course, is there. And .NET 3 is already installed, so you've got that. When we talk about XP, you have to install .NET 3, and the same thing goes for Windows 2003 Server. You can turn on WSAT as well. So you get all of these things in either environment. It's just that you have to install .NET 3 first in the non-Vista or non-2008 server environment. Can you have nested transactions with a WCF transaction, like call a server? Well, there's two questions here. One is, can you nest? And I think, if you mean, can I call downstream services and have multiple different services participate, the answer is yes, as long as they all support transactions. And you can flow the transaction from a service to another service, for example. And then the other question is, can you have a transaction between SQL and Oracle using WCF transactions? And the answer is yes. It's just a matter of the ADO.NET provider that you use, or however it is that you're calling. So in other words, Oracle has a resource manager. And for Oracle to participate in a DTC transaction, then you would need to install a little COM component in the DTC that knows how to communicate with Oracle resource managers. And so those things have been around for a long time. Another question, what would you have to install to run WCF if you're using Vista? Well, Vista comes with .NET 3, so WCF is already installed. You just have to add the web service atomic transaction support. Would it be possible to, okay, so I think that's it for the questions right now. Now, the binding support. Essentially, what we can do is support transactions for name pipe, TCP, web service HTTP, and dual HTTP binding, as well as federation. So what that means is, of course, I can have services that are on the same machine over name pipe, across machines or processes over TCP, and I can flow the transactions to them. But the web service ones are interesting in that if I want to participate in a web service transaction and possibly expose services to the internet that can be included in a transaction from a Java client, it's possible to do that interoperably. Each of these bindings has a default for the transaction protocol to use, which I'll talk about in a minute. Now, transaction flow by default is stable, so you have to enable that in the configuration. You saw me do that. At the client, this makes it possible to flow the transaction to the server. At the server, it makes it possible to receive a transaction. You can also do this in code, by the way. If you construct the binding and set flow to true, then this is a way to do it programmatically. Transaction flow options at the contract, which remember has to be at the client and the service. Transaction flow option can be not allowed, which means you reject transactions. It can be required because you expect a transaction, and it can be just allowed. If there is one, I'll join it. If not, I'll create my own. Now, in terms of using not allowed, this would be potentially if you want to expose services to the internet and you do not want to have your services and operations susceptible to in-doubt transactions in a greater scope, that maybe the clients that consume your services, you don't know who they are, or you don't want an uncontrolled environment. So you might disallow transactions at that point, not allow them to flow for those operations. It also could be that certain operations just should not be put at risk. Now, to make it mandatory implies that you've designed a service that maybe, for example, like a banking service, debit and credit needs to always happen together. But in my opinion, a service contract probably should not be designed that way. You should wrap it into a change counters function, in this case that I'm showing, and change both counters behind that operation. And then that way you control starting the transaction and managing that. So allowed is the most desirable thing to use as long as you're not looking to protect your services on the internet. And this makes it possible to flow a transaction if one is there. Now that means, for example, we might update the example that I have now where each of these operations has a transaction flow option. We allow it at each operation. We make it possible to coordinate setting both counters, but we don't require them to be synchronized, for example. And then we've got counters, which doesn't allow transactions because we don't need one to retrieve the counters. Now, the service operation itself also must require a transaction if you want to join the existing client transaction or if you would like to create your own transaction at this point. And it will autocomplete on default, which means that you don't have to worry about voting. If voting happens as soon as the operation is complete. If an exception is thrown, it will vote to abort. So I just went through all of that, and then at the client must flow transactions, must have a transaction, so you create the scope to flow it, and then you also have to make sure your proxy represents the same settings as the service on the contract. And I showed you how the Web Service Description Language contract describes these things so that when you generate a proxy, it's all there. The protocol options, usually the defaults are satisfactory in that TCP and namepipes use OLE transactions, which means use the DTC. If, however, your namepipes and TCP services need to participate in a web service atomic transaction that was flowed from another platform, then we would need to enable WS atomic transactions. And in .NET 3.5, there's a new update to the web service atomic transactions because we now have a final spec. And so we can choose WS atomic transaction 1.1 as the setting for the protocol. We can also choose the backward compatible one, WS Atomic Transaction October 2004, which was the previous version of the web service specification. The default is to use October 2004 at the moment, because that is what has been in WCF when we first released. So you opt in to the newer version of the spec, which might take a while, by the way, before all platforms are actually up to date with the latest version of the spec. So if you're doing interoperability, you probably care to be using the right one based on who your clients are or services you call. And by the way, it should be documented in the WSDL contract. Now, in terms of setting these options, we set it on the binding directly. So transaction protocol, WS Atomic 1.1 can be set in the binding directly if we want to participate in web service transactions that were flowed from other platforms. You can also set this in code on the binding using the transaction protocol enumeration. As for HTTP, it defaults to October, but you can change the value by using a custom binding. In other words, WS HTTP binding does not provide a transaction protocol setting for you to set at the moment. So we would have to create a custom binding that did HTTP text messaging, the appropriate security settings and all of those things, which I'm not putting here, and then transaction protocol choice. So let's just see how it looks to flow transactions over HTTP then. So what I'm going to do is go to the service, and we will add an endpoint here. And this endpoint will be a WS HTTP binding. And here we are, WS HTTP. Now, in order to provide transaction support, I need to override the binding and set it to WS HTTP, the name, and then transaction flow equals true. And like I said, there is no way to set the protocol here. So it's going to default to October 2004 protocol. Now I've enabled transaction flow. I've already set up the contract at the service to support transactions, but let's go ahead and take a look at this and say mandatory, and we'll say mandatory here, and then we will add it for here and make that allowed. So when I reset the counters, I will allow a transaction, but I'm not going to make it mandatory. And then I'm going to disallow it for the counter, get counter call. And then what we'll do is I'm going to delete the configuration of the client, not the host. I'm going to run the host. I'm going to update the service reference for the client, which will get now the two endpoints. I have an HTTP and a TCP. And now my app config will be regenerated. And so we'll see a TCP binding and a web service HTTP binding. I'm going to give these friendlier names to type in the proxy. So I have two endpoints to hit. And we'll go to the form. And what I'm going to do is actually add two proxies. So I've got proxy TCP and proxy HTTP. So WS-HTTP is the name of the binding endpoint to use. And NetTCP is the one for the original proxy. Now, why am I doing this? Because I'm going to use two proxies separately to call setCounter 1 and 2 as part of this transaction. And then, of course, that will just illustrate that I'm using HTTP protocol for this one, I'm using TCP for this one, two separate channels even communicating, and I'm still going to be able to coordinate a transaction across. So let's go ahead and run that. And we'll reset the counter and set to something successful. Two separate proxies, two separate channels, coordinating a transaction across the two. Now let's set to 12. I get an exception. And, oh, okay, sorry. That's a separate error because I'm recreating my proxy, but of course now when I do that, I have to use NetTCP because we have more than one endpoint. I'm recreating my proxy after exception in this case, just so that we could continue working, right? So we'll just update that real quick. And I think that will do it. Good. And let's run the client one more time. Okay, and we'll set it to 12 again, generate an error. Cannot exceed 10 on the second counter, and it looks like it rolls back because we have a transaction. Now, if we look at the service, we made transactions mandatory. So in fact, if I try to turn off transactions here and here, then we're going to have a problem. That's the client. So we'll try and make a call. Service operation requires a transaction. Now this exception is actually caught at the client without wasting the server's time because the proxy generation process uses the same attributes on the client contract as well. So this is a good thing. And so essentially we are well educated that we need a transaction here. So that was HTTP and also the illustration of two services being coordinated and still being able to roll back when an exception occurs. Let's talk about timeouts. So there's a couple of things you care about with timeouts. Number one, there is a limit on the machine by default in the machine config for system.transactions. And that is that there's a max timeout of 10 minutes by default. You can increase that in the machine config. The other thing that you care about is that there's a default for all transactions of 1 minute. And so the default initialization, if you will, of a transaction scope and or of a service transaction with WCF is going to be 1 minute as well. So we can change those defaults. But those are more global for the whole machine. Now, normally you wouldn't necessarily want a transaction longer than 10 minutes unless you're debugging anyway. And the default of 1 minute is probably not so bad, but you can increase it as needed by initializing the transaction with a longer timeout if you're concerned. And so how that looks is, number one, there is a service timeout for transactions where you can initialize your services that if they create a transaction instead of joining a client transaction, then they will initialize the transaction with this timeout. And this just illustrates making it like 1 second, which would be, of course, inadequate, but it allows you to illustrate failure. The other thing you can do is apply that at the service behavior and set the transaction timeout to 1. Now, it's important to note that these settings, actually what they control is when the service creates a transaction. But remember that if a client application creates a transaction and flows that to the service, then the client transaction is going to govern how long it expects that timeout to be. The other thing that you care about with transactions, aside from timeouts, is isolation level, and that is, by default, services say that they will join the client's isolation level. So if a client flows a transaction to a service and says, I want serializable, then that's what we get. But if they say, I want chaos, then that's what we get. So that's not necessarily very good. Let's take a look at a couple of those things just very quickly. So on the host, what I'm going to do is I'm going to set my binding so that it actually has a receive timeout of 10 minutes, because otherwise we expire always after 1 minute. And we're going to do that as well for the HTTP binding, or the TCP binding. So now I've got a receive timeout of 10 minutes. And that's going to allow me to take a little longer to process the request at the server. I'm going to do the same at the client because, again, my goal here is I want to demonstrate a transaction timing out, not a request timing out, right? So let's go ahead and set the receive timeout, or sorry, the send timeout to 10. And then I'm going to actually do that as well for the send timeout here. So now both of my bindings have a send timeout of 10 minutes, and that will allow the send message to take a little bit longer. Okay, so again, this is nothing to do with transactions just yet, but let's go ahead and take a look at the transaction settings in behavior. So what I'm going to do here is I'm going to set service timeout to, let's say, a second. Now, what's this going to affect? It's going to affect transactions that start at the service. Keep that in mind. Now, what about timeouts from the client? So let's see what happens just with this setting right here. So the service host is running, so I'm going to actually restart that. And then at the client, what we'll do is just take the defaults for now. And we'll set the counters to 5, let's say. And, you know, we can do our usual exception, in which we'll fail and roll back. Everything's good, right? Reset counters, it just works. Why? Because it's not taking that long. In fact, even a second is not long enough. So what I had failed to do, which I had meant to do, is put in a sleep. So just to make this take a little longer, let's go ahead and say thread sleep, and we'll put in here, let's say, 60 seconds. Actually, no, we don't want to wait that long, so let's say 20 seconds. And I'll do that twice. I'll actually also put that in the second counter, and we'll try it again. Run the host, run the client. And we'll call to set the client. It's going to take 20 seconds. And because we extended the receive timeout at the server and the send timeout at the client, we're not going to time out in that respect. Okay, so that works. Now let's call reset counters, which is resetting to 0. And that's going to take the full 20 seconds. However, at some point here, we'll probably get an exception indicating that the transaction actually times out. Okay? So this is reset to 0, and it's still busy. And actually then the timeout is actually taking a little bit longer. So still holding up, not responding. Okay, so basically, I think I just shut this down. Okay. So what I want to illustrate is that from the client, you can actually take the code to set the counters, and you can initialize the timeout here. So transactions information is a type that you can create. And info here, oops, sorry, I meant to say transaction options. And in the transaction options, you can set it so that you have not only the isolation level, and I'll set that to chaos here just to try something out for you, and I'll also set the timeout. And I'm going to make the timeout a lot less, like 5 seconds, let's say. And what we'll do is we'll pass that as a parameter to the transaction scope. So notice I'm using a different isolation level, and I'm controlling the timeout from the client. Okay, just starting the host, I think. Try that again. Oh, I think I'm not compiling. Oops. Just a second. 2 errors. Okay. Not showing me the right error, but I can see here that I need to resolve the transaction isolation level. So that might help. Okay, looks like that works. So let's go ahead and start the host. And now we'll start the client. Now my client is going to, when I set the counter to 5, even something positive, because it takes a while, you're going to see an exception that, oh, well, that's a different issue, and that is it's not liking the enumeration value of chaos. And that is WCF probably at its best saying, we don't like that, because remember, the default behavior for a service is to use the transaction isolation level. So the isolation level is set to, by default, unspecified, and that's fine, but it's not allowing us to pass chaos, so I guess that means I was getting a little wise in doing that. So we're going to go ahead and set that to something a bit more reasonable, like read uncommitted, and try it again. So we'll start the client. And we're setting the value to something that's actually legal, but remember that there's the timeout. The client's saying that any transaction can only last 5 seconds, and I've got a sleep going on for 20 seconds. So now it's saying the transaction was asynchronously aborted. I expected that. That's a good thing. So in other words, the client controls the timeout of a transaction that's initiated at the client. The service controls the timeout for transactions initiated at the service. And you might have noticed that reset counters, even though the transaction timeout for that would have been only 1 second, like I said it in the service, because I forgot to put the transaction scope required here on reset counters, we didn't actually have a transaction. So if I take away this sleep and just run this normally, and then we actually just make one quick other change, so that instead of the isolation level being whatever the client says, I'm going to require that you use serializable isolation level. And with that, I'll restart the service. This is the last little thing here. And the client will attempt to set a different isolation level, and the service is not going to be happy with that. So we'll get an exception here saying that the isolation level is not acceptable. So here are your options. With the service, if you leave the default, you'll join whatever the client transaction level is. But if you would like to enforce your system to be serializable isolation level, to have the best level of consistency, then you should apply that on all your services, and that will force clients to use that level of isolation. Okay, so a couple of things happened there. I showed you some timeout settings as well as some issues related to isolation level. And so just to sort of sum this up, when we think about transactions, remember that you're probably going to have some transactions, obviously within your stored procedures coordinating table access. In your data access layer, you might have a transaction scope that coordinates calls to separate stored procedures and or separate tables or databases. But in your business layer, you may also coordinate calls to multiple data access layers. So you might have a transaction scope here, in which case you probably want to always join the transaction of the root in order to make sure you coordinate well. When we reach the service tier, the way it works is a client might call multiple services. And so a service would then ultimately join the client transaction scope and coordinate all the calls all the way down through the data access layer separately in order to make sure that we leave the consistency of the system state. So best practices would state that every tier, you only worry about your own transaction. What am I coordinating? What am I coordinating? What am I coordinating at the business layer? And what am I coordinating inside a service operation? So this might be a transaction too. And lastly, what am I coordinating at the client, and can I flow the transaction to the service? And so that would be how you'd approach that. So with that, remember that you can get the code, and I have multiple examples for timeouts and other things in the code for my book, which you can get at thatindigogirl.com. And then I'll take a look at the questions and answers. So thanks again for coming to the webcast today. Remember that I'm going to do an MSM webcast in just about an hour. So hopefully I'll see some of you there. Thanks very much.
All right, thank you, Michelle. I'd also like to launch our survey for today so that the attendees can fill that out. So you should be seeing that showing up in your slide area. All you need to do to fill out the evaluation is to click on the links that you see in the middle of the screen. We do appreciate your feedback. It helps us to improve our future webcasts. I'd also like to remind you that you can print a PDF of the slides by going up to the File menu and selecting the Print PDF option. Michelle, are you just going to address any questions via text from this time?
I addressed two very quickly in text, and there don't appear to be any other questions at this time. So anybody, if you have any additional questions or you didn't have time to stay for that, just go ahead and email.
All right. Thank you so much, Michelle, for your presentation today, and thank you, everyone, for joining us. This concludes the audio portion of today's conference. See you next time.